Alright, in this video we're going to talk a little bit about radius of curvature and the curvature value kappa. And so one definition of curvature, kappa, is that it's equal to 1 over the radius of curvature. So for example, if you had a circle of radius 2, your curvature would be 1/2. And just to kind of get a feel for that, let's look at a couple different circles. Let's look at a smaller circle and then a bigger circle, and ask ourselves, as the radius gets bigger, what happens to kappa? So if this one is, let's say, radius 3, and this one only has radius 1, then the curvature kappa for this smaller circle is going to be 1 over 1. So that's a curvature of 1, whereas for kappa for 1 over 3 is actually only 1/3. So the bigger the circle you get, the less the curvature, which seems kind of odd because you'd think, well, isn't the curvature constant? You know, they're both circles. But if you think about it, the change, for example, let's look at the change of two tangent vectors along a given length. I'm going to draw this a little bit bigger. Okay, so here's one of our tangent vectors, and here's another tangent vector, and I'll call this T1 and T2. And between them there is some amount of arc length that I'm going to call S. So that's this arc length between T1 and T2. Now let's draw the same amount of S, let's draw the same amount of distance of S over on this bigger circle. So we still have length S between our two tangent vectors, T1 and T2. But you may have noticed that if we compare these two, let's kind of compare them down here, that if this is T1 and T2 for this circle, and this is T1 and T2 for this circle, you will notice that the smaller circle has gone through a larger angle than the bigger circle. So in other words, across a certain length of segment, you are changing the direction of your tangent vector more, and thus this circle has a higher kappa value, a higher curvature value. So this is kind of an intuitive looking at circles. Let's turn it into calculus. So similarly, we're going to be looking at the change of the tangent vector across some length S. It's just in this case we're looking at an infinitesimal change in the tangent vector over an infinitesimal segment length. And so to do that, we'll take the derivative of the unit tangent vector with respect to S. And in doing so, this can be kind of difficult to work with. You'll notice that most of the things we've done in Calc 3 so far, we want everything to be integrated in terms of time. Because for time, we've got, for example, if this curve is r, it's a vector function r that is a parametric equation of an x component, y component, maybe z component, but all those components are parameterized in terms of time. So we really like to work with time. So how do we change dt ds to something in terms of time? And that is there's a sneaky trick here. So what you will do is you will write, using the idea of the chain rule, you can write this in terms of the change in the tangent vector with respect to time multiplied by the change in time with respect to your curve S. And so you'll notice here that the dt's cancel, and we're left with dt ds again, which is what we started with. But we're expanding this to kind of sneakily throw time in here. So one thing you may notice about ds dt, or dt ds rather, is that it looks like velocity upside down. So the change in s with respect to t, the change in length with respect to time, that's velocity. we have velocity upside down right here. So let's go ahead and write this as 1 over velocity. And remember, kappa is not a vector value. Kappa is scalar, and so we're not going to be taking the vector of velocity. We're going to be taking the magnitude of the velocity and then multiplying it by the change in the unit tangent vector with respect to time. And I believe that's also going to be a magnitude of, because we're not looking for a vector value, and these are both vectors. And so what this is equal to is the value kappa. So this gives us curvature. Well, interestingly enough, at every point on R, this vector function R, there is a kappa value. And if there's a kappa value, there's also a radius value. And so what's really interesting is that we can draw an instantaneous circle at any given point on our vector function here. So I picked this point right here. As you can see, I tried to represent a radius, a circle of a certain radius that seems to fit that tangent or that change in tangent with respect to arc length. And so this is called the radius of curvature for that point. And to find the radius of curvature, we can use the relationship kappa equals 1 over r. So we can solve this function right here, and that'll give us kappa, and then we can do the inverse of kappa and get radius. So in other words, radius equals 1 over kappa. So once we solve for kappa, we can plug it in here, and we can figure out what the radius is at that given point on our curve. And that's it for the radius of curvature. I'll see you next time.